Hello, welcome to the Basics of IBIS Models webinar hosted by Mentor Graphics. I am Arpad Murani and I work for the SDD-BSD High-Speed Product Marketing Group. We will begin our webinar with a background and history overview of how IBIS modeling started. Then I will review of what behavioral modeling is so we can understand the technical details a little better later on. And then we'll talk about the DC characteristics of buffers, which are the IV curves, transient switching characteristics, and diparasitics, package modeling, differential buffer modeling. I'll try to explain how the devices operate so we can understand what the data means that we generate for the models, but I will also give information on how we can generate the data from simulations or from lab measurements to make these models. At the end of our webinar, I will also talk a little bit about new directions, recent developments in the IBIS specification to cover new capabilities. If you looked up the word IBIS in a dictionary, you'll find that it is actually the common name of about 30 different species of long-legged, long-necked wading birds. But in our context, the acronym IBIS stands for I/O Buffer Information Specification. IBIS is actually a specification for a file format and a data format which are used to describe the behaviors of these different buffer models. So strictly speaking, IBIS files are not models, they are just data containers which contain the data for the models which are implemented in the tools, the simulators. Some versions of the IBIS specifications have been standardized, and you can see those numbers on the bottom of this slide. The standardization of the latest version of the IBIS specification is ongoing work in progress. One of my first jobs at Intel Corporation in 1991-92 was to perform all the signal integrity simulations for the PCI bus. A lot of these simulations were performed before we had anything designed into silicon to prove the concepts of the reflected wave switching PCI bus. We knew how the main buffer characteristics could be described with IV curves and edge rates, so we decided that we would make behavioral buffer models to be able to perform these simulations. These behavioral models worked so well in our simulation work that at the end of the project, Intel decided to supply customers with behavioral models together with the chips. But customers were using a fairly wide variety of simulation tools from different EDA tool vendors. This situation made it clear to us that a tool-independent behavioral modeling standard was needed. This is how the IBIS Open Forum was born with about 10 member companies, and the first IBIS specification version was released in April 1993. The latest version of IBIS is currently 5.0, which was released in August 2008. I would like to take a few moments to discuss the differences between behavioral and structural modeling. Behavioral models usually describe the electrical characteristics of a device as seen at their terminals. This is a black box type modeling approach because no internal information of the device is available in the model or even needed in the model. All the characteristics of the device are described by what's observable at the terminals. IBIS models are black box models because they don't use any of the internal details of a device. An interesting analogy is S-parameter models for interconnects. S-parameters are also black box models because they only describe what's seen at the terminals of the interconnect. The data that is used to describe these types of models are usually derived from measurements at the terminals. The measurements can be performed in a lab or with simulations if you have a full structural model for the device. Simpler models could even be made from information available from data books. Structural models, on the other hand, are based on all the details of a device. For example, a SPICE model for a buffer would contain all the transistors that are found inside the buffer and also the connection schematic diagram of how those transistors are connected together. But not only that, they also need the transistor manufacturing information, the process file, that describes how the transistors are made. Continuing with our previous analogy with the S parameters in the previous discussion, a structural model for a printed circuit board trace would include its trace dimensions, the cross-section, the length, the stack-up information, which is the distance from the ground plane, and the material properties of the insulator between the ground and the trace, such as dielectric constants and similar information, which are all processed by the field solvers to make the electrical model ready for the simulation. For the sake of completeness, I also would like to mention the electrical equivalent or reduced circuit models. These are strictly speaking not behavioral models because they are not completely a black box approach. There are some circuit details, but these circuit details have pretty much nothing to do with the original circuit design. For example, a full transistor level buffer model could be simplified into a Thevenin circuit which consists of a voltage source and a series resistor. These two elements are circuit elements, but they are totally unrelated to the content of the original buffer's circuit design. Similarly, a transmission line could also be modeled by an RLGC circuit equivalent, but again, these four elements, a resistor, inductor, conductance, and capacitance, have nothing to do with the original trace that it's intended to model. This slide is an illustration for a structural model, a transistor level SPICE model. The picture on the left side is a schematic with all the transistors in the circuit and their channel widths, channel lengths also indicated on the drawing. The left side is a model file for the transistors, which basically describes the manufacturing process, how each transistor is made. This slide illustrates the makeup of an IBIS model in the form of a block diagram. The two small squares on the left side indicate the connections for the input stimulus and the enable control signal to the model. In some tools, these connection points are not even available for the user. The bigger gray box on the left side represents the control logic for this model. The logic in this box is responsible to control the remaining building blocks of this buffer model to put it into the drive high mode or the drive low mode, or into the receive mode, the tri-stated high impedance mode. From this block diagram, you can see that a basic IBIS model for a CMOS buffer consists of 4 IV curves, 2 ramp numbers, a die capacitance, and a package model. The 4 IV curves are needed to model the pull-up structure, the pull-down structure, and their associated power clamp and ground clamp characteristics. The 2 ramp numbers describe the buffer's edge rates, the rising and falling edges, when it's switching. The die capacitance, the C-comp value, describes all the parasitic capacitance that can be seen when we look into the die pad. There are several different ways to model a package in IBIS, but the simplest package model would be described by a simple RLC circuit for the package resistance, inductance, and capacitance. I would like to turn our attention now to the content and structure of an IBIS file. Each IBIS file starts usually with a header section containing the file name, date, version, source, notes, disclaimer, copyright, and similar information about the file itself. A single IBIS file can contain the modeling data for multiple devices or components. The component keyword followed by the name of the component indicates the beginning of the data in the IBIS file for that particular component. Each component has a package keyword with the default package information, a pin keyword to list all the pin names and the associated buffer model names, optionally listing individualized package parasitics for each pin, and some advanced keywords for differential buffers or programmable buffers. The information needed to describe a component is highlighted with the yellow background on this slide. Please note that one IBIS file can have multiple components, which means that this highlighted area can be repeated multiple times within an IBIS file for different components. Using the next few slides, I'm going to dive into the technical details of IV curves. An IV curve describes the current versus voltage relationship of a device. Let's look at the family of IV curves for an N-channel MOSFET transistor. This transistor could very well be the pull-down structure of a CMOS buffer, but we are going to look at it by itself to understand the IV curves better. The source of the transistor is connected to ground. The drain of the transistor, which would also be the pad in the case of a buffer, is connected to a variable voltage source. We are using this voltage source to force the voltage and measure the current, and we are sweeping the voltage across the entire range where we want to obtain the IV curve. While we are doing this measurement, we keep the gate voltage at a constant DC level. However, we repeat the measurement several times at different bias voltages on the gate. When the gate of the transistor is biased to 0 volt, the channel of the transistor is completely turned off. This is indicated by the green arrow on the plot below. When the gate is biased to VCC, the supply voltage of the buffer, in this case 5 volts, the channel is completely turned on. This is marked by the red arrow on the plot below. These are the two IV curves that we can obtain from a buffer through measurements. I usually refer to the remaining IV curves on this plot as the partially on IV curves. They all correspond to gate bias voltages anywhere between power and ground. These bias conditions only exist for a transistor usually when the buffer is transitioning high to low or low to high. For this reason, it's really hard to obtain these IV curves through measurements or even simulations because we cannot stop the buffer in the middle of its transition to be able to carry out an IV curve sweep. I would like to point out the two diodes that I put on the schematic drawing of this transistor. These diodes are actually part of the transistor's construction, and they are often referred to as the parasitic diodes. They are formed by the p-n junction between the drain contact and the substrate, or the source contact and the substrate. When the voltage on the drain is positive, both of these diodes are reverse biased. This corresponds to the situation when the signal that the buffer sees on its pad is between power and ground. Other than a small capacitive loading, these reverse bias diodes wouldn't affect our signaling at all. On the other hand, when the voltage on the drain goes in the negative direction below ground, one of the diodes becomes forward biased. This forward biased diode will start clipping the signal fairly strongly. This is the area on the IV curve plot that you can see on the left side, marked by the blue arrow. Those strong currents come from one of the parasitic diodes of the transistor. The pull-up structure of a CMOS buffer is usually made from a p-channel MOSFET transistor. The IV curves of a p-channel MOSFET transistor are a symmetric equivalent of the n-channel MOSFET transistor, so I'm not going to explain them again here. Instead, I would like to focus our attention to what we call the VDD or VCC relative IV curves in IBIS. If we performed the IV curve measurements of a pull-up transistor as shown in this schematic, with the voltages being expressed with respect to ground, we would lose the symmetry in the voltage numbers compared with the n-channel pull-down transistor measurements. It doesn't make physical sense to do it this way either, because a pull-up transistor is connected to the top supply rail, and all of its characteristics depend on the voltages with respect to the supply rail and not with respect to ground. An additional complication arises from the fact that IBIS models are usually generated with 3 different supply voltages for typical, minimum, and maximum operating conditions. Keeping that in mind, making ground-relative pull-up IV curve measurements makes even less sense because the IV curves would cross the 0 point on the x-axis in 3 different places for the tip, min, and max conditions of the measurement. For this reason, the pull-up and power clamp IV tables are all expressed in a VDD or VCC relative manner in the IBIS files as shown on the next slide. This slide shows a family of IV curves for a p-channel pull-up transistor measured with respect to VDD, the power supply rail. This arrangement of the IV curves also has an advantage when power supply noise is present in the supply rail of the model. The simulator is not going to have to recalculate the ground relative voltages with respect to the moving supply voltage. It can just simply connect the current source to that supply, and the noise in that supply will be automatically included in the output waveform that way. On the next few slides, I would like to give you a few practical suggestions on how to perform IV curve measurements in a lab and what to watch out for. On this slide, there are two schematic drawings for showing how a device under test can be connected with the power supply and the curve tracer when making VDD relative IV curve measurements. In a normal ground relative measurement arrangement, the grounds of the power supply, the device under test, and the curve tracer would all be connected together. The positive terminal of the power supply would be connected to the device under test, and the positive terminal of the curve tracer would be connected to the output of the device under test. However, in a VDD relative measurement, we would like to have the curve tracer's negative terminal, which is the reference for the IV curve, to be connected to the positive terminal of the power supply. You have to be very familiar with the power supply and the curve tracer that you are using for these measurements. Some power supplies or curve tracers have their negative terminals connected to their chassis ground. If you hook them up as shown in these diagrams, you will create a perfect short between the positive and negative terminals of the power supply, possibly causing permanent damage in the equipment. However, if your power supply or curve tracer has floating terminals, you can connect them as shown in this diagram and make your VDD relative measurements directly. If you don't have the equipment that allows you to connect them like this, you can always take a ground relative measurement for your pull-ups and convert them numerically after the measurement has been taken into a VDD relative representation. This slide illustrates another potential problem that you could run into if you are not using the appropriate power supply for your lab measurements. As I explained it before, the parasitic diodes of the transistors could get forward biased when the signal on the pad of the buffer goes outside the supply voltage range. Since we would like our models to include these effects during the simulations, we need to characterize these parasitic diodes in our models as well. Therefore, when we perform these IV curve measurements, we'll have to force the pad voltage outside the supply voltage range to activate these diodes and get their currents. In order to keep the power supply voltage steady for the device under test, regardless whether the curve tracer is inside or outside the supply voltage range, the power supply must be able to sink and source current. Less expensive power supplies, however, are not able to do that. Therefore, you must pay very careful attention to what kind of a power supply you are using for these purposes, otherwise your data may not be accurate. Another potential problem you have to keep in mind when performing IV curve measurements is the resistive losses in the high current path. The fixturing of high-density devices can add significant amount of resistance in the measurement path. That was a case when I measured 4 or 5 ohms. Considering that stronger drivers can draw tens or hundreds of milliamps of current, and that clamping diodes can draw currents in excess of an amp, you'll see that a few ohms of resistance in the path can cause significant amount of inaccuracies in the measurements. If your curve tracer has a high impedance sensing input, these problems can be overcome by a 4-wire probing arrangement. The sensing input of your curve tracer would have to be connected to the points on the device under test where you are performing the IV curve measurements. If you have access to picoprobing equipment, you might want to consider to remove the plastic covers from your chip and put the picoprobe directly on the die pads of your buffer that you want to measure. If you can't reduce the resistivity of your fixturing to a negligible level, and if you cannot make use of the sensing input of the curve tracer to compensate for these effects, you might want to consider numerical compensations to eliminate these losses from your measurements. In order to be able to perform such numerical corrections on your data, you would just have to replace the device under test in the fixture with a short and repeat the IV curve measurement again with that short in place of the device. This will basically give you the characteristics of your fixturing, and this data can be used for making the corrections on your original data. The correction algorithm is actually not all that complicated. It's just the application of Ohm's law to the two measurements, which can be carried out in a simple spreadsheet type calculation. Since IBIS modeling is a black box approach, we might ask ourselves the question of what buffer characteristics we get in these IV curve measurements. A buffer usually has three different modes of operation. It can be in a receive mode, it can drive high, and it can drive low. We have to collect IV curves for all of these conditions for making an IBIS model. When we measure a buffer's IV curve in its receive mode, we get the characteristics of its parasitic diode currents, the ESD protection currents, any on-die terminations or pull-up, pull-down resistors, static overshoot protection clamps, and anything that's constantly on in the buffer when it's not driving. When we measure a buffer's IV curves in its driving mode, we usually get all those currents that we saw in its receive mode, plus anything else that is dynamically turned on and off. This would include the pull-up structure, or the pull-down structure, or any other dynamic clamping or termination schemes that the buffer might have. The power clamp and ground clamp tables in the IBIS files describe the buffer when it's in the receive mode. The pull-up IV table in the IBIS file describes the buffer when it's driving high, and the pull-down table describes the buffer when it's driving low. Please note that when we measure the buffer's IV curves in a driving mode, the static currents that were visible in the receive mode are still present in those measurements. Since the IBIS pull-up and pull-down IV tables must not include a duplicate of the data that is in the power clamp and ground clamp tables, we first have to make a subtraction of the two measurements before we put the data into the pull-up and pull-down IV tables in the IBIS file. This slide includes a couple of illustrations for what different IV curves might look like. The red curves are obtained from the buffer when it was in the receive mode. The black curves, which are hardly visible, were obtained from the buffer when it was in the driving mode. The green curves are just a numerical difference between those two curves. The IBIS pull-up and pull-down tables need to be filled with the data points off of these green curves. The IV curve related keywords of IBIS are summarized on this slide. Each IV table keyword has a corresponding supply voltage reference keyword, which allows them to be connected to their own independent supply rails. This flexibility is very useful to account for the power supply noises appropriately. These IBIS features come handy also when a buffer uses a different power supply rail for its clamping diodes and its pull-up transistors. For example, a 5V safe 3.3V buffer would have its clamping diodes connected to a 5V rail and its pull-up transistors to a 3.3V supply rail. The IBIS specification requires that the IV curve range should span from minus VDD to twice VDD. In a 5V case, this would mean minus 5V to plus 10V. You might ask the question, why is this necessary? The reason for this requirement is based on transmission line theory. If a transmission line is unterminated, the signal could double in its amplitude at the end. If you had a buffer that was able to drive a 0 to 5V signal swing into the transmission line, the unterminated end of the transmission line would actually double that and you would see a 10V signal. The rules are a little different for the clamp IV tables to prevent double counting. The ground clamp and power clamp measurements on a tri-stated buffer really capture the same behavior in the buffer, except that one measurement is done with respect to ground and the other measurement is done with respect to the power supply rail. For this reason, the clamp IV curve measurements are split in two. The ground clamp table will receive the minus VDD to VDD range, and the power clamp will receive the VDD to twice VDD range. This translates to -5 to +5 in a 5-volt case for the ground clamp, and from +5 to +10 for the power clamp. Note that the IBIS specification doesn't prohibit you from giving a wider range for the IV curves. You just have to make sure that you are not double counting for any of the effects. Unfortunately, the IBIS specification doesn't give us a precise rule on how these ranges should be calculated. For example, the specification doesn't spell out which power supply voltage should be used as the basis for these range calculations: typical, minimum, or maximum. Another question arises with low voltage swing buffers. For example, a GTL driver whose signal range is between 0 and 1.5 volts at most could be still powered by a 3.3 volt power supply. Should the IV curve ranges be based on the voltage swing or the 3.3 volt power supply? Since the IV curve range requirements are based on transmission line theory, I would suggest that you should select the voltage levels of the signaling as the basis for your IV curve ranges. The IBIS specification imposes some limitations on how long the data tables can be. IV curves are not allowed to have more than 100 points per table. The original limitation on the VT tables were also 100 points, but starting with version 4.0, this limit was raised to 1000 points for VT tables. On the other hand, the IBIS specification doesn't require that the data points should be uniformly spaced along the x-axis. This allows the model maker to pick the best points off of each curve that describes its shape the most accurately. The bottom of this slide illustrates an algorithm in a graphical way and shows how the points of the IV curve can be reduced without losing the accuracy in the areas where the curve is changing rapidly. IBIS supports 3 corner conditions for the models. The typical values are required, but the minimum and maximum values are optional. Please note that the minimum and maximum data values in the IBIS file don't always correlate to the slow and fast manufacturing process variations or the worst and best case signal integrity simulation results. Take for example the situation with the IV curves and dye capacitance. The IV curve is mostly determined by the chemical composition of the silicon. The dye capacitance, on the other hand, might depend mostly on the metal deposition on the silicon for the dye pad and for the interconnects between the transistors. These two processes might be independent from each other, therefore a minimum IV curve doesn't always go together with a minimum dye capacitance. Similarly, a strong IV curve, which usually represents a fast and strong buffer, could cause more reflections and ringing in the transmission line, eventually degrading the timing measurements in the signal integrity simulations. For these reasons, the minimum and maximum data points in an IBIS file should be combined in various different ways to find the correct solution space for a design. The temperature keyword in IBIS has a special meaning. For CMOS drivers, a high temperature usually reduces the strength of the driver, resulting in a smaller IV curve. For bipolar drivers, on the other hand, a high temperature increases the drive strength, resulting in a stronger IV curve. For this reason, the temperature keyword should have the higher number in the minimum place for CMOS buffers and in the maximum place for the bipolar buffers. All other keywords in IBIS will have the smaller number in the minimum place and the larger number in the maximum place. The transient or switching characteristics of buffers are described by the ramp or the various waveform keywords in the IBIS file. The package effects should not be included in the data which are made for these keywords. This is easily done in SPICE because we can just delete the package model from our simulations and record the data that way. This might be a lot harder to achieve in actual lab measurements, but there are numerical methods which can be used to de-embed the package effects in those waveforms. The effects of the dye capacitance, on the other hand, cannot be removed from these waveform measurements because the dye capacitance is an integral part of the buffer model. Since the parasitic capacitance effects are already included in these waveforms, we cannot allow the C-comp capacitor in the IBIS model implementation to load these waveforms and slow them down. For this reason, simulators have a special algorithm to avoid the loading effect of the C-comp capacitor on the ramp or the waveforms, while keeping it visible when we look into the buffer from the outside. This slide shows how the buffer should be loaded with a resistor to generate the ramp data. The rising edge measurements of complementary buffers should be carried out with a load resistor connected to ground. The falling edge measurements on a complementary buffer should be done with a resistor connected to the top supply rail. Open source buffers should have both rising and falling edge measurements done with the load resistor connected to ground, and open drain or open sink buffers should have both rising and falling edge measurements done with the load resistor connected to the top supply rail. The values of the ramp keyword are expressed with two numbers, one for dV and one for dt. The values for dV and dt can be obtained from the 20 and 80% points of the waveform which was generated with the resistive load as described on the previous slide. It is very important to keep these two numbers separate in the ramp keyword. In the buffer model implementation, the dt determines how fast the device turns on and off. If we divided the numbers to provide a slope, this information would be lost and the simulation results would be incorrect. The voltage versus time waveforms, the VT tables, are stored under the rising waveform and falling waveform keywords in the IBIS file. These waveforms provide a lot more detail about the buffer's switching characteristics to the simulation tool. For example, a multi-stage slew rate controlled buffer may have humps during the transition which wouldn't be preserved by a simple ramp keyword. Another very important accuracy consideration is that with VT tables we can distinguish between how the pull-down turns on while the pull-up turns off during a falling transition, or how the pull-down turns off and the pull-up turns on during a rising transition. This information is simply not available using the ramp keyword. This is why it is so important to include at least 4 VT tables for a complementary buffer model in the IBIS file. It is also very important to keep the timing relationships of the VT tables for a certain buffer. The beginning of each VT table should correspond precisely to the time when a stimulus crossed the threshold to trigger the transition in the buffer. Please note that the delay at the beginning of each VT table may not represent the clock-to-out delay that is published for the device in the databooks. This depends on how much detail of the pre-driver circuitry is included in the transistor models from which you are generating this waveform. Since the first and last points in a VT table correspond to the buffer being in the steady-state conditions, you also have to make sure that the slopes at the beginning and the end of the VT table are horizontal. Since IBIS models do not support overclocking, you also have to make sure that the length of the VT tables are not longer than the bit time for which the buffer was designed to operate. As I mentioned it earlier, the IV curves describe the buffer's transistors in their fully on or off condition. I also mentioned it earlier that the first and last points on the VT curves correspond to the buffer in its steady state. This means that we can use the waveforms stored in the VT tables to scale the IV curves from 0% all the way to 100%. This information can also be used to check the quality of the model. We can draw a load line across the IV curve using the slope of our fixture that was used to generate the waveform. The intersection of the IV curve and this load line will yield a voltage, and the last point on the waveform has to be the same as this voltage on the IV curve. This three-dimensional surface plot illustrates how the IV curves work together with the waveforms stored in the VT tables. The vertical axis is the output current of the buffer, which is plotted against the output voltage and time. Ccomp is the IBIS parameter to describe the die capacitance as seen from the die pad. This includes all the parasitic capacitances of the buffer's transistors, the metal capacitance that connects the transistors with each other and the pad, and the parallel plate capacitance that is formed by the pad. You should never include the package capacitance in Ccomp because the package is modeled in a different section of an IBIS file. I would like to mention here that an accurate Ccomp is also very important for driver models because the reflections which bounce back from the driver are very strongly influenced by the Ccomp value. You should also be aware that full transistor level models are not always accurately describing the die capacitance. This might happen because they don't always include all the metal interconnects that are found on the die or the metal capacitance formed by the die pad. This slide shows the importance of having an accurate capacitance value even in the driver model. The waveforms are an overlay of a full transistor level simulation and an IBIS simulation. The waveforms on the bottom left were done with an IBIS simulation in which Ccomp was a little bit larger than the total capacitance seen in the transistor level model. The waveforms on the top right show the same simulation, but the IBIS model's Ccomp value was adjusted to match the transistor model's parasitic capacitances. There are quite a few different methods that can be used to measure the die capacitance of a certain device. While some of these techniques give simple answers, others can give more details, such as frequency dependencies or voltage dependencies in the capacitance value. My favorite capacitance measurement technique in the time domain is what I call the forced sawtooth method. In some ways, this method is very similar to IV curve measurements because we force the voltage and measure the current on the output of the buffer. But the main difference here is that the voltage source applies a sawtooth waveform to the buffer and the slopes of the sawtooth waveform are very steep. In order to be able to calculate the capacitance, we are going to have to record the current readings on the rising side and the falling side of the sawtooth waveform at the same voltage points. Knowing the slope of the sawtooth waveform and having the current readings at different voltage points, we can calculate the capacitance for each one of those voltage points using the equation where current equals capacitance times the slope of the waveform. This allows us to create capacitance versus voltage plots as shown on the right side of this slide. Another one of my favorite capacitance measurement methods is done in the frequency domain. I call this one the biased frequency sweep method. In this method, we connect an AC source with a DC bias to the output of the buffer, and we are measuring the imaginary part of the current. The capacitance is then calculated using the imaginary part of the current divided by 2 pi f and the amplitude of the AC source. If we repeat the AC sweep at different DC bias levels, we can generate a nice surface plot, which is the capacitance versus frequency and bias voltage. I want to mention here that both of my favorite methods will work whether the buffer is driving high, driving low, or whether it's in the receive mode. Recognizing the importance of power integrity simulations, starting with IBIS 4, Ccomp can be split up into 4 parts, one for each IV table. We can modify the measurement setup discussed on the previous slides a little bit so that the currents are measured through the power pins. This will allow us to calculate the capacitance for each IV table separately. Using a very similar setup, we can also measure the common mode and differential mode die capacitance in differential buffers. For this measurement, we are going to use 2 AC sources, which are connected to each of the outputs of a differential buffer. We'll set the DC bias of both sources to the same level. One of the AC sources should have a 0 AC component, while the other AC source should have a small amplitude for the AC sweep. This way, the current measured in the 0 AC source will give us only the differential components of the capacitance, while the other source will give us the total capacitance including the differential and common mode components. We can obviously calculate the common mode capacitance from these measurements by employing a simple subtraction. The IBIS specification, however, doesn't support frequency and voltage-dependent capacitance data. So you might wonder, what should we do with all this data that we can generate with these measurements? I would recommend to pick a value that is closest to the conditions in which the model is going to be simulated. For example, if your buffer model is used in gigahertz simulations, it wouldn't make sense to use capacitance values which were measured at a few megahertz only. Similarly, you should pick a capacitance value from a voltage range that matches the signaling levels of your simulations. On the other hand, if you need a more accurate model, you might want to consider the AMS language extensions of IBIS. The IBIS specification has several different keywords for package modeling purposes. The package keyword is required in IBIS. This keyword contains a typical minimum and maximum RLC value for the entire package of the component. The minimum and maximum value is supposed to represent the shortest and longest traces inside a package. The pin keyword allows you to enter a unique RLC value for each pin. Since the package information provided under the pin keyword provides a more detailed description of the package, these values will override the values found in the package keyword. The package model and define package model keywords can be used to make even more detailed package models. Because of its higher accuracy, if there is a package model keyword in the IBIS file, it will override the package information found under the pin or the package keywords. This slide illustrates the two methods which can be used to describe packages under the define package keyword. On the left side, you can see the multi-segment uncoupled transmission line approach. This method allows you to model multiple segments in a package, but doesn't allow you to include the coupling between the traces. The example on the right side of this slide illustrates how the same package model can be described by resistance, inductance, and capacitance matrices. This approach allows you to include all the coupling effects between the package traces, but the entire package is described by a single set of RLC matrices. In the early days of the IBIS specification, most differential buffers consisted of two single-ended drivers which were driven in the opposite direction by the stimulus signal. The diff-pin keyword can be used to associate two single-ended buffer models to act as a differential pair. This approach works really well for all differential buffers in which the pad-to-pad currents are negligible. The example on the bottom of this slide shows how this syntax works. I usually refer to buffers which have significant pad-to-pad currents as true differential buffers. These types of buffers can be modeled in IBIS by separating their differential and common mode characteristics. The common mode characteristics can be described by the regular model keyword. The differential mode characteristics can be described using the series keywords in IBIS. If these keywords don't provide you the capabilities that you need to describe your differential buffer, you might want to consider the AMS language extensions in IBIS. After learning about all these technical details, you might wonder how you are actually going to sit down and write your own model. First, you have to collect and generate all the necessary data for your device. This can be done through simulations and/or lab measurements. But not all of the information that goes into the IBIS file can be generated from simulations or lab measurements. Some of the information may have to come from the data book or from the specification of the device. Once you have collected all the data, you'll have to do some processing and formatting to conform to the IBIS requirements and rules. This could be a tedious job if it had to be done manually. Fortunately, there are several free and commercially available IBIS modeling tools, but to my knowledge, none of them achieved 100% automation for the model making process. A very important step in your model making process is to check your models when you are done. The IBIS Open Forum provides a free golden parser program which checks for syntax errors in your IBIS files. The golden parser, however, cannot check for the correctness of your data. For this reason, you should always run some simulations when you are done with your models to make sure that the waveforms are correct. The source code of the golden parser is also available at a cost for those who wish to implement it in their software products. Mentor's Hyperlinks software comes with a Visual IBIS Editor utility, which includes the official IBIS golden parser as well. This is what Mentor's Visual IBIS Editor looks like when you first start it. You can navigate in the file conveniently using the tree structure on the left side, which lists all the keywords and subparameters in the file. You can also execute the golden parser on your file and see the various warnings and errors on the bottom of the screen. The Visual IBIS Editor can also plot the data that is found in the various tables of your IBIS file. This webinar was designed to discuss the basics of IBIS modeling. However, before we close, I would like to mention some of the more important recent developments in IBIS. The IBIS 5.0 specification came out with a new algorithmic modeling interface to support multi-gigabit per second SerDes simulations. The statistical and signal processing techniques in AMI models allow simulators to generate millions of bits worth of simulation waveforms in just a few minutes. The IBIS Open Forum is about to release a new specification called the IBIS Interconnect Subcircuit Specification. The IBIS ISS specification standardizes all the passive elements of HSpice with the permission from Synopsys. Together with the Touchstone 2 specification, which is also the result of the IBIS Open Forum efforts, these new capabilities will bring much needed improvements to package and buffer modeling in IBIS. In closing, I would like to summarize the topics we covered in this webinar. We began with a short history of how the IBIS Open Forum was formed and reviewed what behavioral modeling is. Then we discussed in great detail how the DC and transient characteristics of buffers can be modeled with the IV curves and VT curves. Then we went over how the parasitic dicapacitance can be measured and modeled in IBIS. We also talked about package modeling and differential buffer modeling in IBIS. At the end, I mentioned a few recent developments in the IBIS Open Forum and the new directions we are taking with the IBIS specification. I hope this webinar was useful for you, and I want to thank you for attending.